Assalamualaikum warahmatullahi wabarakatuh. Hi everyone, today we are going to learn one case study from gas absorption process, which is packed absorption column. Acetone is being absorbed by water in a packed tower having a cross-sectional area of 0.186 meters square at 293 K and 101.32 kPa. The inlet air contains 2.6 mol percent acetone and outlet 0.5%. The gas flow is 13.65 kgmol inlet air per hour. The pure water inlet flow is 45.36 kgmol water per hour. And film coefficient for the given flow in the tower are 3.78 times 10 to the power of minus 2 kgmol per sm3 mole fraction. And for the single mass transfer coefficient for liquid phase is 6.16 times 10 to the power of minus 2 kgmol per sm3 mole fraction. The gradient for the equilibrium line is 1.186, and these are the question, which is to calculate tower height using K prime YA, K prime XA, K capital prime YA, HG and NG, and also HOG and NOG. So first of all, to answer for A, B, C, D and E, what you need to do is to draw the graph first. So basically, how to solve this kind of question is first you have to draw the diagram of the packed absorption column, which is like this. Okay, this is a diagram for packed absorption column where it contains of two main streams, which is gas stream and liquid stream. The gas stream that will enter to the packed column we denote as V1 and the outlet gas is V2, whereas the inlet solvent or inlet water is L2 and the exit solvent is L1. And you have to denote the composition for each stream, which is for V1 it denotes as Y1, V2 Y2, L2 X2 and L1 X1. And these are the information given in the question, which is the surface contact area is 0.186 meters square, the temperature, the pressure, the single mass transfer coefficient in gas, and also single mass transfer coefficient in liquid. As we know that this system is operating in a dilute solution, so the liquid flows in is equal to the liquid flows out, and also same with the liquid inert, which is L1 is equals to L2 is equals to L prime is equals to 45.36 kgmol per hour. And since the question gives you the equilibrium gradient, so that value is used to develop the equilibrium line, which is YA is equals to MX. So you just take any values of YA in your graph and substitute into the linear relation, which is Y equals to MX, and then you will get M is equals to 1.186. Alright, and this is your relation, and from this linear relation we can develop the XY data to plot the equilibrium line. Okay, and the next step is to plot the operating line. So in order for us to plot the operating line, what you need to have is two coordinates, which is 0.1 and 0.2. And as you see in this diagram, okay, coordinate for 0.1 is actually refers to x1, y1. Coordinate for 0.2 is x2, y2. And we only yet to know the value for x1. So that's why we have to solve x1 using its material balance. So this is the material balance for packed absorption column, where you can find it in your appendix, which is L prime times x2 over 1 minus x2 plus V prime y1 over 1 minus y1 is equals to L prime times x1 over 1 minus x1 plus V prime times y2 over 1 minus y2. What you need to do is just to substitute all of the values which have been given in the question into this equation and solve x1. Next, you will get x1 is equals to 0.006479. The next step is to develop the operating line. Since we have already know the value for x1, y1, so then we can locate where is your 0.1, and x2, y2 you can locate for 0.2. So you have two coordinates, which is to develop the operating line. After this, I will show you what your graph looks like. Okay, next is we have to find the slope. in order for us to find slope, we have to use the equation of slope for pack absorption column, where this is the equation of the pack absorption column, which is minus k prime x a over 1 minus x1 over k prime y a over 1 minus y1. And the original equation of slope for pack absorption column is actually this equation, where we have to find the value for 1 minus xim and 1 minus yim, which is we don't already have the value for xi1 and yi1. That's why the first trial we have to use this equation. Since we have already know the value for x1 and y1 from the material balance, definitely we can find the value for pm1, which is minus 1.6. So using the linear relation, which is ymx plus c, we can calculate for the y-intercept for the first trial of slope, and you will get the value for 0.0364. And then if we see of your graph, okay, let's see the graph. These are the graph. Okay, this is your equilibrium line and this is your operating line, and the y-intercept is situated over here, which is 0.036. And then what you need to do is just to join this point up to P1, because we use the coordinate for P1 to substitute in the equation ymx plus c, and then use the same gradient until it reach equilibrium line. And the intersection of this slope with the equilibrium line is actually the yi1 and xi1. Okay, and next is to verify this slope is accurate enough, we have to use the value for yi1 and xi1 to be inserted back into the original equation for a pack absorption column, which is this equation for the second trial, right? Minus k prime x over 1 minus xim over k prime y over 1 minus yim. So you have to solve for 1 minus yim and 1 minus xim, and these two equations we can get it from the appendix. y1 and x1 is already in the question, which is in your material balance. yi1 and xi1 is from the previous value, you get it from the graph. So then you can solve for this equation and this equation, which is 1 minus yim is 0.979 and 1 minus xim is 0.9901. Just substitute into the original equation for pack absorption column. Then you will get the then you will get the value for equation of slope for pack absorption column, which is minus 1.61. And if you see the value for PM1 for the second trial and value for PM1 for the first trial is close each other, and then we can say that the slope is accurate enough, meaning that if you still continue to the next step, which is to find the y-intercept for minus 1.61, you will get the same value of C, and of course you will get the same value for xi1 and yi1. So you can say that this graph is accurate enough, and this is your latest value for xi1 and yi1. The next step is to develop the second slope of the graph, which is to get the PM2 line. Since we already have the value for PM1, which is minus 1.61, we can use that gradient to get the coordinate for PM2 line, which is what you need to do is just to find the coordinate at the x-axis using the same gradient. So again, can use the value, we can use the equation for ymx plus c, where your y will be the 0, is because the coordinate at the x-axis for y is 0, and m is, you take it minus 1.6, and x is, we want to determine the value for x, and y-intercept, which is for c, is the y-intercept for the second slope. Okay, we see the graph. Okay, so this is the second slope, where you have to develop this slope using the same gradient from the previous graph. Okay, and then this is the y-intercept for the slope, which is 0.05, which is the coordinate for P2 y-axis. And what you need to have to get the coordinate at x-axis, it means that the value for x, we have to find the value of x, and the value of y is 0. So that's why in ymx plus c equation, you have to state that y is equals to 0. This is m minus 1.6 times x plus y-intercept 0.005. Then you will get the value for x, 0.003. And this is the coordinate for the PM line, which is 0.0030. So you just plot in the graph and drag from P2 to this coordinate. Then this would be your second slope. And after you get the second slope, then you can find the xi2 and yi2, where the intersection of PM2 slope with the equilibrium curve, okay, is the value for xi2 and yi2. After you get the value for xi2 and yi2, you can find also the y2 star and x2 star, y1 star and x1 star based from this graph. Why we just want to calculate or to identify this value is to solve for question number C, D and E, where you have to use the overall mass transfer coefficient in gas and liquid. Okay, and next is to find the xi minus xm, where we have to calculate this equation, and this equation is the last equation that you should apply to calculate z is this equation, right? Let's say for A, VAV over S, y1 minus y2 is equals to K prime YA, Z y minus YIM. So let's say you want to solve this equation. So VAV is actually from the question, already in the question, S already in the question, y1 and y2 is from material balance, K prime YA is from the question, Z we want to determine the Z, and y minus YIM. So to solve y minus YIM, this is the equation. y1 minus yi1 minus y2 minus yi2. See, the y1 and y2 is already in the material balance, and yi1 and yi2 you get it from the graph. So if you don't have the tools of slope in your graph, you cannot find the value for yi1 and yi2. Since we already have the value for yi1 and yi2, you just substitute into this equation, then you can get the value for y minus yim to be resubstitute back into this equation. So to make your steps easier, you just rearrange the equation, make z as the subject. So then it will be easier for you to do the unit cancellation. And VAV is actually the V average, where V1 plus V2 over 2. And make sure the unit of volumetric flow rate for V and also the mass transfer coefficient is standardized. Based from this question, the unit for mass transfer coefficient in hour, unit hour, and for volumetric flow rate V1 and V2 is in second. So you have to standardize. You just divide with the 3600 second, and then after that you will get the value for VAV, which is this value, and then substitute into the equation, then you will get the value of Z using single mass transfer coefficient in gas phase, which is 1.946 meter. And next, to calculate for Z using single phase mass transfer coefficient in liquid, you have to find the value for xi minus xm, and the equation for xi minus xm, you can see over here, is xi1 minus x1 minus xi2 minus xi2 and so on. And again, x1 and x2 we can get from the material balance, and xi1 and xi2 you can get from the graph. Okay, we look over the graph again. xi1 you get from the slope number 1, which is intercept on the equilibrium curve. This will be your xi1. xi2 is from slope number 2, which is intercept on the equilibrium curve. This is xi2. Just substitute back into this equation. L average is actually the same value, since it is dilute, L1 is equals to L prime is equals to L average, and then you will get the same, actually almost the same value using the single mass transfer coefficient in liquid, which is almost 2 meter. Okay, we will continue to learn on how to calculate the tower height using K capital prime YE and HOG and ROG in the next video lecture.